In the next video, I will show you how you can find the partial derivative of z with respect to x and the partial derivative of z with respect to y for this equation. In this video, I'm just going to show you some basic notations that you need to know first. So back in single calculus, we would have some sort of function where you have one input and it would do some sort of computation and then it will spit out a y value. But here we have the right to write an equation as a mixture of x, as a mixture of x and y, as a mixture of x and y. So in single calculus, we can differentiate this by doing something like this: 12y squared, and because y is a function of x, we would need to stick dy by dx in here. We've already done this, and I'm expecting you to know this. In multivariable, you have two inputs coming in. So in this case, it's two inputs, x and y, and it will do some sort of computation, and it will spit out a z. So you can think of z as a function of x and y. So in this situation, we do have the right to write an equation as a mixture of x, y and z. We do have the right to do this. So when you come to differentiate this, because which I will show you in the next video. So when you come to differentiate this, you differentiate z as normal, so that would be 2z. But then because z is a function of x, so if you're trying to find this thing here, you would need to times the partial derivative of z with respect to x. And I will elaborate more on this in the next video. Don't worry about this for the time being. So when you have a function, or when you have a function looking like this, you do have the right to write an equation as a mixture of x, y and z. Looking at this, I need you to understand this notation as well. So when you read this, it's some sort of function acting on x, y and z. So some sort of function, so this could be anything, some sort of function acting on x, y and z, acting on x, y and z. But looking at this thing here, z is determined, is governed by the input x and y. So what that means is so currently this thing here describes this equation, but you need to be able to train your mind to visualize it in a different way. So the same function here, we can imagine it as this form here, where it would spit out a new variable, let's say w. So you have three inputs, x, y and z. So if you look at this here, you've got a mixture of x, y and z. So this is me trying to teach you that you can reimagine the same equation in a different way. So as opposed, instead of imagining it in this way, you can imagine the same thing in this way here, where z is governed by the x location and the y location. So that's this thing here. So this is your z here, but it's governed it's governed by x and y. And then so you've got this machine here. By the way, these two machines are equivalent. So you got this machine looking like this, and then it spits out a new output. So you can imagine this output as being, I don't know, some sort of scale here: 0, 1, 2, -1, -2. So this is your w, the output. So let's say you input three variables, and then it will spit out let's say a -2, or it will spit out some sort of value 1. But in this case, it spits out a value of 0. So if you imagine this situation here, you have to imagine the whole thing spitting out a value of 0, specific value of 0. It can't spit out a 2. So it can't spit out a 2. It can't spit out a -1. It must spit out a value of 0. So you have a choice. You can either imagine it as this thing here, where you can just write the whole thing, or you can imagine it in this form here. So in this form, you have to know that z is governed by x and y, and then when it spits out the value w, the value w must be a 0 if you were to visualize it in this manner. So what that means is this. Hang on, let me just elaborate on this. So let me just show that z is governed by x and y. So hang on. So what that means is this. Imagine you're designing a drone in 3D space. So you've got a small house here located at 10, 9, and then you've got a tree here. You've got a tree here located at 6. Let's say, hang on, 6. Let's say 2 here, 2 here, and then you've got a tall building located at whatever. Let's say 1 and 5. Say. So what that means is, looking at this thing here, you see z is a function of x and y. So what that means is the height of the drone is governed by the x location and the y location. So if the drone is currently at 10, 9, then make sure the drone is at a height of, let's say, I don't know, 10 meters. If the drone is at the location 6, 2, which is above the tree, make sure the height of the drone is 20 meters above the ground. So here you eliminate the height. You just need to know the x location and the y location of the drone. Or if the drone is currently at hang on. If the drone is currently at, let's say, 1,5 is at the building. So make sure the height of the drone is 30 meters above the ground. So this location, this height here, is determined by the x and y location. But as far as the machine is concerned, the machine only requires where the location of the drone would be. So in the x location, it would be, I don't know, 1. In the y location, it would be 5. And then in the z location, which is a height, is 30 meters. But who cares about this 30 meters? We only need to know the x location and the y location. So you input the precise location of the drone, x, y, and z, and then it will do some sort of computation. Let's say it takes the temperature at that given point. So the output here, we can imagine the output as being the temperature above the building. So that's what it means. So when you look at this, some sort of function, but then this function here is so this, you can think of this as being the height where it's governed by the x and y location of the drone, and then it will do some sort of computation to work out the temperature at that precise location. Okay, so when you have a machine looking like this, hang on. When you have a machine looking like this, let's just ignore this for the time being. So you've got the x. So this is a different scenario where you have x location, y location, and the height, and then it will do some sort of thing to work out. Let's imagine it as being the temperature at that precise location. You could have a scenario where R and S will determine the x location, R and S will determine the y location, R and S will determine the Z location. So let's imagine R represents the battery life of a drone. The battery life of a drone. Let's imagine this is, I don't know, atmospheric pressure at a certain atmospheric pressure. It's just a number. So these two things will determine where the drone should be. So if the battery is low and the atmospheric pressure is at, I don't know, let's say, I don't know, some sort of number, let's say 20, then the drone must be in this location, and in this location, and then it will work out its temperature. So in this case, when you have a machine looking like this, you can imagine the function as being like this. Hang on. Let's just hide the x, y, and z. So you can imagine it as being, well, x, y, and z exist somewhere in this machine. Well, here you've got two inputs coming in, and then it will spit out one output. So in this case, it will be partial derivative of w with respect to the partial, well, with respect to r. So it's a partial. But then if you have something like a new variable coming in which determines r and s, but then r and s will determine the x location, r and s will determine the y location, r and s will determine the z location. So here you can imagine this thing here as being like a machine looking like this. Hang on. You input t and then it will just spit out w. So here you write the direct dw, normal d, direct w with respect to dt, because here you've only got one variable coming in, whereas down here you've got two variables, whereas here you've got two variables which will determine the temperature. So in which case you have to write partial derivative of w, because you've got two variables coming in, 1, 2, then you have to say with respect to the partial derivative with respect to s. In this case we're doing it with s. Here we're doing it with r. The point I'm trying to make here is that in this scenario here, because you've got two variables coming in, one must be constant and the other one must be a variable, in which case you have to use a partial derivative. Up here you've got one coming in and one coming out, so it's just like a normal function. So in which case you can just use a direct dw and a direct normal dt. Okay, so there's a difference between the two. So in the next video we're going to work out the partial derivative of this. Okay.